This is a re-upload of one of the videos that I've made in the past about the Lax Milgram theorem and the application that this theorem has to the Poisson equation. One of the subscribers noticed that I am using I'm using the L2 norm and not the H1 norm when I prove the coercivity result. So in both continuity and coercivity of the bilinear form, I will use H1 norm for consistency to be concrete and consistent. Lax Milgram theorem is a theorem that shows well-posedness of partial differential equations and is very useful for this elliptic problem, for this elliptic equation with zero Dirichlet boundary conditions. And gamma here denotes the boundary of the region omega, which is Lipschitz. I have also denoted the spaces that I'm working with. So U is the solution of this differential problem, and phi is the test function that I'm going to use in order to obtain the weak formulation of this strong form. And the function f is at the right-hand side is a function that belongs in the L2 space. So the H1 means that the norm of the function in L2 and the gradient is bounded. H01 means that the norm of the function and the function are bounded in L2, and also the function vanishes at the boundary. The function space L2 is the space of a square integrable function where the norm in L2 is finite. I'm using these spaces for function u, function phi, and the function f. So I need to obtain the weak formulation of the Poisson equation. I multiply with a test function, and then I have to integrate over the region omega. Now here I use Green's identity. So I have the boundary integral of the function phi times the gradient of u times the normal vector, the outward vector associated with the boundary of the omega, minus the integral over omega grad u grad phi d omega equals minus the integral over omega f times phi d omega. Now my function is in H01, the test function, which means that it vanishes at the boundary. And what I end up is having is the integral of over omega of grad u grad phi d omega equals minus the integral over omega f times phi d omega. The weak formulation is finally written in this form. Where u is in H1, phi is in H01, and f is in L2. Now, this is the bilinear form is the left-hand side of this equation. This is the bilinear form. And this linear functional is the right-hand side. I'm not going to use it here. For the Lax Milgram, I will need the bilinear form. Is the integral over omega grad u grad phi d omega. This is also grad phi grad u d omega. So it's B P U. This bilinear form is symmetric. And now what I need to do is to, for the Lax Milgram, first is to show the continuity of the bilinear form. I take the absolute value of the bilinear form. So this is grad u grad phi d omega. And this I can use the integral inequality for it's a triangle type inequality. The integral of the absolute value of grad u grad phi d omega. Then I can employ the Cauchy-Schwarz inequality. So I take that this is the grad u in L2 of omega times the grad phi in L2 of omega. And this is less than the u in H1 and times the norm of phi in H1 of omega. The norm in H1, let's assume that you have the H1, the norm in H1 squared is the norm of u in L2 squared plus the norm of gradient of u in L2 of omega squared. And similarly, the norm of phi in H1 of omega squared equals the norm of phi in L2 of omega squared plus the norm of the gradient in L2 squared. So I have used this expression for the H1 norm in order to obtain this last bound here. And now I'm going to show the coercivity of the bilinear form. Coercivity. I take B u of u. So it's the integral over omega grad u d omega. And this can be written as absolute value of grad u squared d omega. This is, I take square root of this quantity and then squared, because this gives me immediately the norm of gradient of u in L2. And this I can write it as a half of the norm in L2 squared plus a half. Yes, I can write it like this. Now I use the Poincaré inequality, which says that the norm of u in L2 is bounded by a constant times the norm of gradient of u in L2. Now I reverse this inequality. And this is greater by 1 divided by c norm of u in L2. So here this is greater than 1 over 2 c squared times the norm of grad u in L2 squared plus a half, sorry, this is not the grad u norm, is the u norm in L2. And here is the grad u L2 omega squared. Now this is greater than beta times u in L2 of omega squared plus the norm of grad u in L2 squared. And of course, this bit is the norm of u in H1. where beta is just the minimum of 1 divided by 2c squared and 1 divided by 2. So I have showed the coercivity and continuity. Continuity plus coercivity gives me a well-posedness of the Poisson equation of the bilinear form. I hope that now you are satisfied because I have used in the previous video I have used the L2 norm to obtain the coercivity instead of H1, and now I think I have closed this previous gap. Thank you again for your remarks. I really appreciate it, and it seems that you have well you have a good knowledge of the topic.